Welcome to The Explainer. Today, we're diving into a huge problem in science and medicine, and honestly, in pretty much every field. What do you do when you have way too much information? Okay, so here's our game plan. First, we're going to really understand the problem itself. Then, we'll explore 3 super powerful data science tools to tackle it. And finally, we'll look at the incredible real-world impact this is all having. All right, first things first, we have to wrap our heads around this core challenge that data scientists are constantly up against. It's something they call the curse of dimensionality. I mean, think about it. We are just swimming in data these days, right? From every sensor, every study, every click. But does having more data automatically mean we have more knowledge? Not always. And here's the really weird part. When you have hundreds or even thousands of variables, what we call dimensions, all of our normal intuition just goes right out the window. The things that seem obvious in our simple 3-dimensional world, they just don't work anymore. So take a look at this. This is a famous classic data set, and it only has 4 dimensions, and it's already just crazy, confusing mess of plots. Now try to imagine this with 400 dimensions, or 4,000. It's literally impossible for a person, or even a computer, to really see the true patterns hiding in all that noise. All right, so how do we actually deal with this? How do we find the signal? Let's bring in our first tool. It's a classic, tried-and-true technique called principal component analysis, or PCA for short. So the whole idea behind PCA is to boil down all those messy variables into just a handful of new variables, these principal components. And the trick is, these new components are designed to capture the most important information, the most spread in the data. It's kind of like creating the ultimate, super concise summary of everything that's going on. What I really love about this is how it breaks down what sounds like a scary algorithm into 3 simple geometric ideas. First, you just center the data. Easy enough. Then you rotate it around to find the best possible angle, the one that shows the most variation. And then finally, you just project it. You squash the data down onto that new, more insightful view. And wow, this is the perfect before and after shot, right? On the left, you've got that confusing matrix we saw earlier, total mess. On the right, after PCA does its thing, you get this beautiful, clear plot. The 3 different species of flowers just pop right out. We've gone from total noise to a clear signal. Okay, so PCA is awesome. It really is. But it's not perfect. It has one major weakness. It's looking for straight line patterns. So for data that's more tangled and complex, we're going to need something a bit more modern. Right, because what happens when your data isn't a nice, neat cloud of points? What if it's all tangled up, like these knots and rings you see here? A simple straight line summary from PCA just isn't going to cut it. It won't tell the real story. And that's where this technique, TSNE, comes into play. You know, its goal is actually pretty simple to understand. It just wants to make sure that if 2 data points are close neighbors way up in that complicated, high-dimensional space, they stay close neighbors when we map them down to our simple 2D screen. It's all about preserving those local relationships. And I mean, just look at this comparison. It is incredible. On the left, PCA tries to visualize a famous dataset of handwritten digits, and it just gives us this useless, overlapping blob. But on the right, TSNE completely untangles it. The result is so clear, you can practically read the numbers, right? You can see the cluster for zeros, the cluster for ones, for eights. Each digit has its own little island on the map. Okay, so we've talked about making these really cool, insightful pictures out of our data. But what if our goal is different? What if we actually want to build a model that can make predictions, and we want to know which factors are the most important for that prediction? Well, for that, we turn to techniques called lasso and ridge. You can kind of think of them as disciplinarians for your model. They add a penalty for complexity, which forces the model to focus only on the variables that truly matter. And the key difference, as you can see, is that lasso is the tough one. It can actually force a variable's importance all the way to 0, effectively kicking it out of the model entirely. Okay, this is super cool. The secret sauce for why lasso is so good at this is all in the geometry. So imagine the best possible model is at the center of those red ovals. But lasso forces the answer to stay inside that blue diamond shape. And because the diamond has these sharp corners, the solution is way more likely to land right on an axis, and when it does that, bam, that variable's importance drops to absolute zero. Ridge's circle is smooth, so it doesn't have that same power.
And you can see it happening in real time right here. As we crank up that penalty, that's the lambda value on the bottom axis, Lasso just starts automatically pushing the coefficients for less important variables down. Watch how the line for things like college education gets squashed until it hits zero and vanishes from the model. It's like automatic spring cleaning for your data.
So we've gone through a lot of pretty technical stuff. PCA, TSNA, Lasso. So what? Why does any of this actually matter in the real world? Well, the payoff for being able to tame this data beast is absolutely huge, especially in medicine. Just think about this. In a real study on tuberculosis, researchers had data on 425 different metabolic variables for every single patient. No doctor on Earth could sort through that and find a pattern. But using the exact methods we've just talked about, they could cut right through all that noise and find the specific biomarkers that could signal the disease. And this stuff isn't just theory. It's the engine that's driving the next generation of medical AI. It's powering everything from getting more accurate diagnoses to creating personalized treatment plans to even speeding up the discovery of new drugs. And this right here, this is the future. We're talking about AI agents that can see a patient's health in all its crazy complexity, learn as new data comes in, and help doctors make decisions with insights that were just impossible to get before. Which leaves us with this one kind of mind-blowing thought. By learning how to tame this data beast, we're not just making clearer charts or better models. We're opening the door to a whole new era of proactive, predictive medicine, one where we might just be able to spot diseases